So, all right, so my pleasure to introduce Harry Sweeney. So Harry was my PhD advisor back from 1987 to 1990, I believe it was, 91, at the University of Texas at Austin. I was very fortunate to have found Harry from California. Unlike now, I guess I only applied to 2 graduate programs and I got into 1, and I moved to Texas without ever having been there. So that was quite different than people's paths these days, Harry, don't you think?
Yes, many people apply to several.
And actually, most of the people in this class are seniors, and I know at least a few of them are headed for grad school afterwards, Harry. So,
and you should say it's not an irrevocable decision. I applied to several places and got into Ohio State and arrived there and quickly realized it was not a good fit. So I started the process a second time and went to Johns Hopkins, which was a very good experience. So,
yeah, that's right. And I guess especially, when you say fit, probably one of the things that means is finding a mentor where your research interests and their research interests are well aligned.
Yes, that was one of the reasons I was interested in Ohio State. There was a physicist there who was doing some very interesting work at low temperatures. And I got there and discovered he was just in the process of retiring. So,
well, and also, unless you know the person, you can imagine arriving at a place and after having met with them, and you might realize that their personalities and yours don't mesh.
Absolutely.
So here I sent you a couple notes of what I thought we'd chat about. So this whole course is titled Making Physics Experiments. And we would be making lecture demos in hands-on labs if we were on campus and not all at home. But, we have lectures where I talk about various technologies and aspects of experimental work and design and measurement and control, things like that. And I thought you and I could chat about the subject of how does one choose a research project, which you have done many dozens of times, if not many more than that. And I've done at least a dozen times, choosing research projects and research directions. And, I was fortunate coming to graduate school that you had a project in mind that was well meshed with my interests that we could work on. I probably wasn't ready coming into grad school just to be able to choose an entire project that ordinarily, of course, the PhD mentor helps the student come up with a project that works for one. So, yeah, we have these questions we could look at, but any initial thoughts on that whole subject, Harry?
Well, it's a very hard decision to make in the choice of a project. Can I just give a little background? When I went to New York University as assistant professor, I intended to do research that would be built on the research I'd done as a PhD student on behavior near a critical point, equilibrium phase transitions, where it was a big project to measure the scaling of a behavior of some property, like the compressibility of a fluid, or say the magnetization of a magnet as you approach the Curie temperature, where the magnetization goes to 0. But I got to NYU and started setting up to do that. And Ken Wilson announced a theory, Kenneth Wilson, a physicist at Cornell, that pretty much settled the whole question. It unified the understanding of ferromagnets and fluids. And so it was much less interesting to embark on a career of studying what had been pretty well settled.
Less mystery, less to discover.
Right, less to discover. So I started looking around for new directions. Biophysics was becoming popular. Astrophysics was popular. And so I started off, since I knew something about laser light scattering, to study properties of viruses in solution as a biophysics project. And I published some papers. And I teamed with a theoretical astrophysicist who was studying the interstellar medium, and there were questions about the temperature of the interstellar clouds, but the temperature would be determined from the line widths of different molecules. Anyway, I measured in CO, carbon monoxide was a molecule. It was a good fingerprint for that temperature. So I set up and put together a tandem spectrometer and an interferometer to measure the line width as a function of pressure, published in Astrophysical Journal. And that looked like a possible direction. But then I heard a lecture about studies of systems driven away from equilibrium. How would how would one characterize transitions from one state, the equilibrium state, or a continuation of the equilibrium state to some new state? Would there be well-defined transitions, and how would you characterize it? And so I set up to do with colleague Jerry Golub to do an experiment on a fluid, and actually in the same system, type of system Dan used in his PhD thesis. A fluid between rotating cylinders. You rotate the cylinder, say the inner cylinder, faster, and at some point there's a transition, very well-defined transition, where waves, where pattern appears in the fluid. And that's that type of study has been my whole career, essentially, to look at transitions in systems driven away from equilibrium. But the point is, I went in three directions, not really having a clear plan in any one of them, but just to explore them, and one worked out.
Well, and just to make a comment for the class, if you have a rotation where everything's rotating at the same rate, that's actually an equilibrium condition. So a rotating planet with no changes in rotation rate is equilibrium. But if you have a system with different parts rotating at different rates, so-called differential rotation, that's away from equilibrium and often leads to instabilities and mixing and waves and vortices and all sorts of
phenomena.
Exactly. Yeah, and I guess when I started as an assistant professor, I also had a plan for 3 different research projects. And in the end, 2 of them turned out and 1 of them didn't. So I dropped 1 of them early on and then went forward to study surface wave excitations and droplets and sprays, you probably recall. And then the liquid metal experiments that I continue to this day. So when I started out, I was already thinking about the geophysical side of things. So, well, and so one of the things that one could look at in thinking about starting new research is just what are the outstanding unanswered scientific questions? What are the gaps in knowledge that exist today? And so Harry, in thinking about that, how would you go about detecting gaps in scientific knowledge?
Well, I was thinking about that when you raised the question. I mean, I attend seminars, I read, at least scan Science and Nature, and talk to people, and ask that question to other people. Listen, talk to theorists, talk to other experimenters, attend conferences. I often got ideas from the attendance of the conference. Just go and listen to talks, and with the thought in the back of my mind, is there something that I might do to contribute to the understanding of the problem the person is presenting?
Well, and in reflecting on that, I realized that sometimes it's obvious, and in a paper they'll even have a section saying unanswered questions or new directions. Sometimes it's a little more subtle, in the sense they may say something using that word may. It may be that the tidal inertial internal waves shape the continental slope. And when they say may, they're saying that this is a hypothesis. We're not entirely sure. Maybe somebody should check this. And then the other thing I've noticed is that, and this is my own personal observation, is that if you're reading literature on a subject and people describe some cause and effect change using exactly the same words with no variation, I sometimes wonder whether they really understand what they're saying or whether they're just repeating what they've read or what they've heard without any question in any test. It's, in chatting with some of the senior theorists that I'm close to, I definitely have come to understand that all knowledge is provisional in science, or more generally.
And as you think about questions you might address in a research project, you think about what can you bring to the table, and what is your research style? What do you enjoy doing? And I can go to talks about black holes and talks about beyond the standard model, which I have heard many times, many variations of that. And they can be very interesting talks, but they're not something that one could do in this kind of experiments I like doing, which is something on a tabletop, which can be done with relatively modest investment and with a few students, not a team of 1,000 scientists.
Well, yeah, so that's, and I think finding projects that align with a person's skills. So, trying to self-identify, what is it I'm good at that I could bring to a question, and if you're working in a team, what is it this team is good at, that then picking problems that we could make progress on in a way that could be locally unique, right? So if you're a specialist in rotating fluid flows and there's a new rotating fluid flow problem, well, you might consider working on that, especially if you have a lab full of gear ready to go with that.
All along the way in your courses, you pick up theoretical techniques. In your lab work, you pick up experimental techniques. So you build a toolbox that you have. You learn something about spectroscopy, you learn something about temperature control, and you want to think of problems that you can use tools from your toolbox and maybe add to your toolbox, but different experiences in different situations. If you really work, you build up an understanding of Fourier analysis. You build just a lot of theoretical and experimental techniques. And
the interesting things about skills is that, as far as I can tell, we're always at any given decade, any given time, in a special time in science, because there are always recent theoretical advances that may allow us to understand things we couldn't understand. And there are almost always new technologies that have come to bear where, prior to the laser, there just were some things that were not easy to measure. And now, of course, advanced imaging has come a long way. So there are things you can measure now with imaging that would just have been impossible to see prior to that. Well, another example is terahertz technologies are developing very rapidly. And so there are things you can measure in the terahertz that were just not measurable 10 or 15 years ago. So essentially, we're always at some special time in science, which is kind of cool.
Yes, well, things like you're doing with big data, there's opportunities that just weren't available without the ability to examine large data sets.
So another angle to choosing a research project, Harry, that I partially understand, but it's extremely subtle, is trying to get a sense of, okay, I've got a project in mind. I sort of have a sense of how I might do research on it, but I think it may be important to ask the question, is this an important question, an important subject? Is it, if I get the results I'm looking for, will they be important? What are your thoughts on that?
That's a tough question. I think and often we're motivated by questions that a number of people have discussed. And so we know there's some interest in it, but we also do exploratory experiments that were not designed, targeted to address a particular question, but just to understand some phenomenon. May I give an example? We studied the growth of dendrites in the 1980s and found that the dendrites had a fractal non-integer dimensional structure and a fractal dimension of about 1.7. And later, we were studying torn plastic sheets. If you tear something like a garbage bag or the cover of a CD or something, then it stretches and you look at the edge of that sheet and it has waves within waves within waves on that edge. And and you measure the length of that sheet as a function of of the distance from the edge, and you find it's a fractal, just as it was found that in measuring the coastline of Britain in the 1920s, that if you use a smaller and smaller length scale, you get a larger and larger length. And now we say, well, coastlines have a typical fractal dimension of 1.25. But the plastic sheets and the dendrites had both dimension 1.7. And then we started looking at leaves, went to the grocery store and bought some kale and looked at the fractal dimension of the edge of the kale, and it was 1.7. And there's a simple mathematical model developed by Whitten and Sanders in 1981 that gives a fractal structure, and it's also 1.7. So I've wondered why does this dimension 1.7 keep appearing? And there's no answer to that. It's an open question. But that question arises after looking at another problem we looked at was growth of bacterial colonies. And they have, well, the edge of the growing bacterial colony under some conditions is a fractal, and it has dimension 1.7, curiously.
You know, that reminds me of something that I've pursued on and off throughout my career, which is, you know, I look for coincidences.
Mm-hmm.
And
Yes.
you were talking about fractal dimensions, and you know, and you know, sometimes a coincidence is just a coincidence, right? Serendipity happens, and okay, so, you know, those things are unrelated. And I guess the standard phrase is coincidence does not imply causality.
Mm-hmm.
But sometimes things are a coincidence because they are causally connected. They have a similar origin, a similar underlying mass structure, a similar forcing, you know, a similar organizational rule. And so I think it's reasonable in looking for research projects to look for unexplained coincidences and see if there is a way to go about testing whether there is a causal connection or not.
Mm-hmm.
You know, one example that I can think of from the research in my lab is that we've done many experiments in rotating fluids where we ended up seeing waves. Well, you too, right? In the red spot experiment, you had various waves. And, you know, after a while, I came to appreciate that none of that was a coincidence, and that rotating turbulent flows are generically wavy because of the Coriolis restored waves and inertial waves. And you know, the funny thing about that is that you probably recall, Harry, how we saw in the big experiment that the Earth's rotation caused waves to occur in the fluid that were right at the rotation rate of the experiment. So initially when we saw them, we're like, oh, that's kind of a strange frequency to have appear in the data.
Mm-hmm.
And so then I come to understand that in many labs around the world, then people doing rotating fluids experiments, they often had measurable peaks at the rotation rate of their experiment, and they would just never go look at it like, oh, it's a coincidence, it's some fluke, it's some, you know,
Mm-hmm.
even though in many of those cases it was the Earth's rotation directly influencing their experiment that give rise to that precessional peak. So it's kind of like a Foucault pendulum. There's just this forcing that occurs overall. So,
But the coincidences can be merely that, a coincidence.
oh yeah, I know.
An example that I set a student off to measure as a PhD project was the waves in the flow between concentric cylinders that appear above a certain rotation rate of, say, the inner cylinder with the outer cylinder at rest. You get waves that travel, and they travel at 1/3 in the experiments that have been done, 1/3 the speed of rotation of the cylinder. And Richard Feynman in the Feynman lectures says there is an interesting problem. The ratio of two small natural numbers, 1/3. And so I set Greg King off to measure that. And I said, well, that was for a particular radius ratio of the two cylinder radii. What if you change the cylinder radius? And so he constructed inner cylinders of different radii, made a series of measurements, and found that the ratio of the frequency of the waves to the frequency of the cylinder varied continuously from whatever 0.4 on down. And that the particular value that had been used in the experiment that observed the waves was just a happen choice.
Right.
And there was no special significance, even though Feynman made the conjecture. There's something deep there.
So I want to go back to this question of what makes a research project potentially more important. And the standard measure, of course, for us professionally as to whether research is important is whether other research papers cite the research. Citation counts are scrutinized and analyzed. And it's a reasonable measure in the sense that if one's research influences another person's research, then they're more likely to cite your original research. And you've made an impact by them being able to build upon what you've done. I guess another type of impact.
Can I interject?
Yeah, sure.
I'm very unhappy with the great emphasis put on citations on papers when people come up for tenure or promotion and so forth. Because if it's something that's really new, like Einstein's 1917 predictions, then it could take years to observe those gravity waves. And there were almost no citations for 75 years to Einstein's prediction of gravity waves. And I can take a personal example that a student, Andy Fraser, looked at a method for using information theory to make an optimal choice of time delay and reconstructing a phase space attractor from a time series. So from a time series, of course, you have a single variable, could be many different quantities in a system. You take a single variable and it's varying in time, and you can take the value at some instant and then look at the value at some time later, and you've got an XY coordinate, and you can look at then how that XY coordinate moves as time evolves. But you could take different time delays and the picture you would get would be different. How do you choose the optimal delay? Well, that was a question that hadn't been addressed, but the student, Andy Fraser, said, well, we could look at Shannon's information theory and calculate the mutual information. And so he did, and we published a paper. And the student went on to position in Seattle, in Washington, and faculty position. But the paper had very few citations. For 12 years, they're just very small. And then people started noticing it. It now has about 5,000 citations. Wow. Because it's been used, the Andy Fraser's methods used in many different fields in analyzing data.
Well, and I appreciate your point, Harry, that, that also the Lee and York paper on chaos was not rapidly observed. And Ed Lorenz's original paper was completely ignored for at least 10 years on deterministic aperiodic flow. But my point was more general, but what if it has no impact in 1 year? What if it has no impact in 10 years? What if it has no impact in 100 years? What if it never has any impact ever, Harry?
This is possible.
You might agree that's suboptimal.
Yes, I totally agree.
So what that does mean, though, is that when we do research that others may use, short term or long term, either way is fine. That's a better project. And so spend a little bit of time to think about, who is this going to impact? How is it going to impact science?
Yeah, well, every paper you write, you think, who's going to be interested in this? Who cares? I'm writing one
Who
today,
cares?
and I wonder, are people going to read this? Who cares?
Yeah, maybe that's the basic question that addresses the whole thing. Who's going to care about this? And sometimes that can be people in one's immediate field. Sometimes if you're building instruments, that could be people across a variety of fields that could use a new measurement technique. And what I've noticed is that sometimes you can do things that will be good analogies in people in very distant fields. And so they might care about it because, they saw waves. We also have waves. We're totally different discipline, but it's good that somebody outside of our discipline's also been seeing this.
Yes, and I mean that's also done in our designing experiments. We hear a talk or read a paper in some other field, and we say, well, wonder if you could use that method in this experiment or project I'm working on.
So, Harry, I want to wrap up in just a minute, but one of the things that I observed when I was in graduate school, and this could just be my imagination, but I think not, is that you picked many experiments in a way that intentionally or not led to unexpected results, led to seeing something that you didn't necessarily knew was there before you did the experiment. Mm-hmm. And so that's something that I've pondered on is, in picking a research project, I think one goal, depending on one's style, is to pick a project where the chances of discovering something that you didn't know was there is higher. Mm-hmm. And I guess I've kind of enjoyed trying to do that. Go ahead.
Yeah, well, I think both approaches to just explore with the idea that there might be something there, but in other situations to really go with a focus after a focus on a problem which has been there, maybe predicted theoretically, but not observed. And that was the case, for example, in this prediction that Alan Turing made in 1951, that in his last paper, in fact, that one might understand how patterns form in biology by looking at chemical systems which could spontaneously form a spatial pattern. And he had a little model that gave, with a mechanism that gave a spatial pattern. And it was Turing, it was Turing patterns. But so people began to look for them, and decades passed. In the 1980s, nobody had observed a stationary chemical pattern that arose through a transition, a bifurcation, in the way Turing imagined. So in 1984, I was on leave to the University of Bordeaux and talked with some chemists there about Turing's paper. And we decided we would try to observe a Turing pattern. And we worked in design of experiments. Long story short, 7 years later, in 1991, we published a paper in Nature on the first observation of a Turing pattern. So,
yeah. So one style of research then would be to go test predictions or that have not been observed. Another style is in the precision measurement realms, or many find colleagues at NIST and otherwise, then
Yeah.
just trying to eke out another digit or two of fundamental constants and other measurable things. But another style of research is more exploratory, where we're going to go set up a system that's perhaps analogous to something in nature and just observe what occurs with a variation in parameter.
Yeah.
And the tricky thing about that latter thing is that you might not have a specific hypothesis that you're looking for. And so one has to look at the data and say, well, what is it in this data that is surprising? What is it in this data that we might not already understand? And then can we develop a new set of questions just based on that?
If you have several control parameters, you might have a multidimensional control parameter space, and you can start to explore different parts of that space. And it's likely something new will pop up, a transition or a new phenomenon.
So, all right, very good. Now, I guess I want to give a chance to see if anybody in the class has any questions for Harry and or I, or the two of us to both comment on. Lucy, we got an X from Lucy. Was that? Oh, that was a no. Okay, got it. All right, so not seeing any questions. Oh, Nick, you had a question?
You guys hear me all right?
Yes.
I guess one of my questions would be either undergraduate or graduate. What do you think is the biggest thing they do or don't do when they are in their early stages of like career exploration, whether that's research or basically what they're going to do with their first job outside of their studies?
Could you just say the question one more time, Nick, to make sure I understand?
So basically, what is the one thing that you commonly see students do or don't do when they're doing their early career planning?
I mean, I guess that, one of the things that I observe is that many people don't have a plan. Some do and some do not. And so that, of course, as a course, each of you are going to have a chance to chat with me about thinking about the plan. Harry, anything come to mind?
I think that students often don't really take advantage of the opportunities there are for different experiences. To go as an undergraduate, say, on a RU project at one place and then have a different kind of job, say with a company. I worked for a 3M company one summer, and I worked another summer in Washington. You can just get different experiences in different laboratories in the same department, for example, and learn how different groups operate and learn how you interact with different kinds of people, and you learn new skills and how to do deal with different types of instrumentation and different types of issues that arise.
Quinn, I see you have a question. Go ahead.
Okay, yeah. Earlier you mentioned I guess like if you had certain skills, you would pick a project based on what skills or what you've researched in the past. I was wondering if you guys had thoughts on like at what point you develop those skills, or if like later on in your career, is it harder to completely switch to a different area of physics that you haven't gone to, or if you guys had anything to say on that.
Harry, you want to go first?
Well, you can pick up new directions if you have some security in your job. That's one of the wonderful things of tenure. You can pick up different directions. I mean, I talked about going into biophysics or going into doing chemical experiments. I didn't know chemistry very well and not done any chemical experiments. So working in different areas of biology and plant growth. I, through my whole career, worked in different directions, as Dan mentioned, but my style was to have a project that was going reasonably well, maybe 5 years, maybe with funding from the government, and then take up a new project on something I didn't know much about. And I did that repeatedly through the years, just from hearing a colloquium or just reading something and it sounded interesting. Why? And we have certain tools, and can we possibly contribute to the understanding of this problem?
Yeah, and I guess I enjoy learning new things all the time. So, of course, I started out as a physicist studying turbulence, and then was warmly greeted into the geophysics community and working on magnetic field interactions with rotating metals. And then one year I found that my lab had a low temperature experiment in it, and I had to learn low temperature techniques. And that was interesting, challenging actually, to become a low temperature experimentalist mid-career. And yeah, you know, and on, I guess. But brushing up on my Python skills just in the last few months. You know, I know other programming languages, but since I had to be debugging students' work in Python, I thought I should pick that up as well. And so I think, you know, to a certain extent, you know, you can be developing skills throughout your entire career.
You should be.
Yeah. So Jorge, I see Jorge's joined the class. Did you have a question, Jorge?
Can you hear me?
Yeah.
Yeah. So my question was for a friend, obviously. What advice would you give to someone who's applying to graduate school without a clear idea of what field of physics they want to go into? I mean, I seem to hear about other people applying and wanting to go specifically in this and specifically in that, but I haven't really made that decision yet. So, I mean, my friend hasn't made that decision yet.
Harry, what would you say to that?
Well, I would say you go to any large department. I would be inclined to go to a larger department where you have a lot of different projects, and you can look at it, have many choices, and you can see many styles of research. And we haven't talked about picking a mentor, but for a PhD project, that's very important too. You have many choices in a larger institution, but I don't know how many large PhD granting institutions, Dan, 50?
Yeah, it's probably 50 large research physics departments, and that's true across STEM.
Yes.
Well, and I guess, Jorge, I would say, you know, in some sense, it's good to have a plan. So you might want to go ahead and just at any given time have a field that's your current favorite, but have one or two other fields in mind in case you want to switch later on. You know, we talked about developing skills. If you have a plan in mind, you'll have a more focused time at gaining knowledge and skills than otherwise to make that plan come to fruition.
But I would say from the students I've talked to in graduate school who had a plan when they entered graduate school, a significant fraction, I would venture to say more than 50%, graduated in a field different from the one they had in mind when they entered.
Yeah, and it's possible to switch advisors within a department, it is possible to switch fields as well, but you'd have to reapply into a different department.
Or you can work in physics, but do your research in another department. We have a number of students, and you probably had students, Dan, from engineering. I've had students from engineering and chemistry, number of areas of
Applied math.
Right, applied mathematics.
Yeah, I currently have a PhD student from applied math and a PhD student from electrical engineering in my group.
Mhm.
Oh yeah, one from geology too. So I have a pretty cross-disciplinary group right now, which is good because they all bring a different perspective and knowledge overall. So any other questions for from the class on the subject?
Yeah, I guess so you said that, you know, sometimes papers never get cited at all. So the question you might ask is like, so you're thinking about short-term and long-term benefit. It's like, how can you how can you decide whether or not something will ever be useful or not? Or do you just kind of have to go at it and hope that it gets cited somewhere, somehow later?
Harry, you want to go first?
Well, if you're working on a project, you will start giving talks at APS meetings, 10-minute talks, and maybe seminars in your department, and you can gather from response of the audience and talking with others, whether the project raises questions from people. Is there an interest in it? And I think you have a pretty good idea when you write a paper and send it off, whether it'll get many citations. Is it a new method for addressing coronavirus? I think if it is, it will get a lot of citations. But if it's something a project you've thought of, which is not closely related to anything that others are doing, then maybe not, but you could make the project interesting, and you can feel the waters well before you write the paper by giving seminars and talking with others about it.
You know, and I would, you know, given Harry's earlier comments and the reality, I think it's probably not very good to focus on citations, but focus on the notion of impact. That is, if this succeeds, if it goes where I think it's going, who's going to find it interesting, who might be able to use it, how does it make an impact? And that impact could be simply on, you know, for instance, a lot of the work that's done in astronomy, much of their impact is just in raising the awareness of how beautiful a universe we live in and the fantastic things that occur there. Sometimes that impact might be something more technological, where we do a project and it involves a new technique that others can literally directly use, be it numerical or experimental or theoretical. And I think that Harry's right. I actually probably still will often go and talk to people about research projects that I'm early on in, and just gauge whether A, is it interesting, B, was this addressing a problem. And you could, if you really listen to people's feedback, you can tell from that. Yeah. And that could be between fields as well. So you can go to, if you think it's going to have an impact on another field, ask somebody, you know, to tell them what you're working on and just gauge their response overall.
Mm-hmm. Yeah, I suddenly remember a story that I heard from one of my community college physics professors. She said that she was working on her master's in Italy, and it was right around the time, oh gosh, I don't know. She said that they were focusing on, I think, particle physics at that time, and she was more interested in biophysics, but then she couldn't find any professor who would want to, you know, help her with her project for biophysics. And so she ended up having to do a project for particle physics. But then she said that like 10 years later, all of a sudden biophysics became more important. And then she's like, well, so what happens if you end up with that situation where it's like you were interested in a topic that somehow later on got more interesting?
Let me try that one, Harry. So I think the issue there is you got to find your people. Right? If you're sitting in a lab filled with particle experimentalists who are fine folks, and you want to do biophysics, you're just sitting in the wrong lab. And so, you know, and to make that very personal, the reason that I applied to the University of Texas at Austin was because I saw some of the work that Harry's lab was involved with. Like, you know, I think those are my people. So don't be afraid to move, I guess.
Yeah, I was in, as a graduate student, in with a group of students who were very excited about high energy physics. And my desk mate got an internship at Brookhaven National Lab, which was a top high energy physics lab at the time. And he went off for the summer internship. When he returned, I was really excited to hear what he'd done for the summer and what was it. And he said, man, it was boring. He said, I spent the whole summer soldering wires in a wire chamber. And he then changed fields, and he went into condensed matter physics, but grew crystals for his PhD. And he became the eminent crystal grower of the world at Bell Labs. And people all over the world wanted him to get a crystal for a new material or a nicer, bigger crystal of some material that was already well established. Anyway, he found his niche.
Yeah, that's a good way to describe it, right? So, finding your niche is meaning finding an environment of like-minded people who have projects that you fit in, you find interesting, or aligned with your skills and interests and otherwise. And if you find yourself in a place and you ask yourself, is this a good niche for me? And the answer is no, you might want to be looking for alternatives.
Yeah.
So, all right. So I don't see any other hands or questions. So I guess it did end up taking up the whole period, Harry. I greatly appreciate your time. I owe you a bunch.
That was fun.
So, and I know that 2 of the class have signed up for 2 p.m. and 2:30 p.m. career chat with me. So I'm going to go ahead and end the class, and then with those individual students come back at 2 p.m. and 2:30 p.m. to chat with those. So, all right, everybody give me a thumbs up on the participants list. Jorge's quick. Jorge, you're not even enrolled in this class. What are you doing here, Jorge? Good to see you, Jorge.
I'm a guest student. You can have guest lecturers, guest students.
Well, you're the most polite Zoom bomber probably in the history of this month's online education system, Jorge. All right, bye, everybody.
Bye.